In this video I'm going to go over the S2 Edexcel International paper from June 2016. The first question is clearly Poisson, because the word rate, we've got a rate of 9 per hour. Let's call it Poisson, call it X and call it Poisson 9. Okay, a little bit unsettling start I would say for right at the beginning with some wording at some slightly confusing wording. It says a probability that the school website receives fewer, that means less than, V visits in a randomly selected one period is less than 0.75. And then it reverses the thing and says the largest possible value of V. So, as I say, slightly unsettling for the first question. What I'm going to do is use this piece of information first of all and find the the number which is just below 0.75 from the table and write down what that represents in terms of probability, and then take it from there. Let's say a bit of a hard start for the beginning of the paper, but let's go to the tables. So if we just scroll through these questions, get to the tables, lots of things to get through. Let's find a page number whilst we're at it. There we go, that's the normal. And the S2 formulae, go through all the binomial stuff. And here we go, it's going up. And it was Poisson 9, I think we were looking for. And we were looking for the first one where it was under 0.75. So let's have a look. Here's the number, 0.760. And I note that the value of X is 10. For that. So I'm going to go back and write what that represents in a moment. So that says probability that X is less than or equal to 9 is equal to 0.76060. That's what the number in the table I've just shown represents. Now back to the question. This is the first number that's below 0.7060. So this is the largest that X can be, but here's a sting in it. I say it's not nice. It says that it has to be fewer than this number. So if you like, we could say X has got to be less than 10 is equal to 0.7060. So V equals 10. Not very nice for 1 mark right at the beginning. Part B. Find a probability that in a randomly selected 1 hour period, the website receives at least 4, but at most 11. We're on slightly happier territory here. We've got to be careful with the inequality. It says at least 4, so that means greater than or equal to 4, can be equal to 4, but at most 11, it can be equal to 11, so that's that. Now, using this, we can find a probability that X is less than or equal to 11, take away, and then we've got to take away less than or equal to 3, so that we get the relevant probability. You've got to be very careful with the with this type of thing, but it says less than or equal to 4. So if we take away this number here, we're effectively taking away the numbers 0, 1, and 2, 1, 2, and 3 from that. So that gives us the required probability. So let's go back to tables again to look for those numbers. Okay, so the number for less than or equal to 11 is 0.830 there. And then the number for the 3 is 0.0212. So 0.8030 take away 0.0212 is equal to 0.7818. Okay. So that's the answer to part B. Let's look at part C. It's now talking about a 10-minute period, and one of the things about Poisson is we can just change the value of lambda accordingly. There's no lambda we can say is 9 divided by 6, which is equal to 1.5. So we're going to let y be equal to Poisson 1.5. Okay, so y is Poisson number 1.5. It says find the probability that the randomly selected the score receives more than 1. Okay, so probability that y is more than 1. Okay, so that's the same as, I sometimes prefer to change it to a non-strict inequality, but you don't have to. Y is greater than or equal to 2, but that's basically the same as 1 minus the probability that less than or equal, y is less than or equal to 1. So this, it's the way I find it easier not to make mistakes if I change any strict inequality to a non-strict inequality and then work from that, because then we're always doing the same thing. But some, including some students I've taught in the past, find it perfectly okay to go from here to here. So that's just up to you. The second bit is optional. So that's equal to 1 minus 0.5578. If I look at the numbers from the tables, I'll get that number. Take my word for it this time, hopefully. So that's 0.4422. Okay. So now another question where it's changing the rate for part D. Using a suitable approximation, find a probability in a randomly selected 8-hour period. It's more than 80. So now we've got lambda, okay, equals to now we're timesing it by 8. So that's 8 times 9, which is 72. Let's call it W now. W be equal to Poisson 72. Now that's not a number that's in the tables, not particularly easy to work with. And it says find the probability that there's more than 80. So let's say probability that W is more than 80, which is equal to the probability that W is more than or equal to 81. Now we're going to use the normal distribution here. So we're going to approximate, the approximation for W will be the normal distribution with mean 72 and variance 72. Okay, standard deviation square root of 72 and variance 72. So we're going to use that, but we need to use a continuity correction. So because we're going from a discrete to a continuous distribution, when we change it to a non-strict inequality like that, as I say, we're always going back from the, as I've said before in a previous video, we're always going back from the number line, if you like, 80, 81. So we always extend the line further back from where the arrow of the number line would go if you're representing that. So that's actually going to be 80.5. So that's approximately equal to, if I call, so that means that's approximately equal to, if we're standardise that now, Z is greater than, and the 80.5, because of our continuity correction, take away 72 over the square root of 72. Okay, now that equals the probability that Z is greater than or equal to, it doesn't actually matter whether it's strict or non-strict here, 1.00 and some other digits. So that's going to be equal to 1 minus the probability that Z is less than that number 1.00. So I need to go to the normal tables and find that number. So I'm going back through the tables. By the way, I'm not in the habit of using calculator for these, but you are allowed to use the calculator. There'll come a day soon in these courses where these tables will become obsolete, but I don't know, I actually find them quicker to use than the calculator, to be honest. So you can use a calculator if you know how to use it. Anyway, we're going with the tables. So that's 1.00, 0.8413. Okay, is the number we're looking for. So that's 1 minus 0.8413, which is 0.1587. And that's okay to leave it like that because they know you've read it from tables. If you've used a calculator, apparently the number comes to this, 1.5824, which is why the actual mark scheme allows any finite rounds to 0.159 or 0.158 because of the difference between using a calculator or using the tables. Okay, that is question 1 done. Let's have a look at question 2. There's a bit more mapsy questions. For some of us that's a bit of a relief when they're not asking us to interpret stuff in real situations. Here we've got a binomial, which is 10p, binomial 10p, and it says write down the probability that x equals 3. Okay, well the binomial formula basically, the binomial coefficient goes like this: p to the r times 1 minus p n minus r, or such like. So in other words, this we've got n is 10, so we've got the number 10c3, so probability that x equals 3, like that, is equal to 10 C3, 10 because it's the number of trials, 3 because that's our number of outcomes, times by the probability of success to the power of 3, times by the solid probability of failure, which is 1 minus p, because that happens 7 times because we've had 3 successes and 7 failures. And so that's that. Now 10C3 is 120. Which you can find on your calculator. Okay, so that's the first question done. The second part to part A, it says find the value of p such that x equals 3 is 16 times x is 7. Whenever we have that, I always think the main thing is that one thing, we've got to be very careful that we have the expression the right way around. This px is 16 times this. So let's get the right way around. It's 16, px equals 3 is 16 times bigger than px equals 7. Now px equals 3, we've already got an expression for that. That's 120 p to the 3, 1 minus p to the 7. And for px equals to 7, that's also 120 because it's a binomial coefficient. I'll write it out for you just in case. It's going to be 10c7, but that's going to be equal to 120. Now this time we've got 7 occurrences and 3 non-occurrences, 3 times where it doesn't happen. Okay, so the 100, as I said, this number here is 120, so I'll write that in there. 120, and then we may as well cancel the 120. So let's just tidy that up before we do anything else. P cubed 1 minus p to the 7 equals 16p to the 7 1 minus p cubed. Now I can do a bit of division here and divide it through. If I divide through, let's just do the cancelling first. The p cubed can cancel with p to the 7 to give me p to the 4. And the 1 minus p cubed on this side and the 1 minus p to the p to the power 7 on this side can also cancel to give me 1 minus p to the 4 on this side. So that's a bit of a mess. So let's write that out again with all the cancelling bits done. We have 1 minus p to the 4 equals 16p to the 4. Right, I'm aware that p will be a fraction, so I'm going to write it this way around. I don't suppose it really matters. If I take the 4th power now, I can take the 4th power of this. So we've got 1 minus p equals 16 to the power of a quarter times p. Well, 16 to the power of a quarter is equal to 2. The 4th root of 16 is 2, so I can do that. And so therefore I will have 3p equals to 1, so p equals to 1/3. Okay, so a little bit of work to do for that question. And then we've got part B, which is it's a similar type of thing, but this time it's for a Poisson. Okay, so let's just do that. It says that we've got Poisson lambda, and it's saying, giving us a similar kind of scenario, where the probability of y equals 3 is 5 times the probability of y equals 5. So py equals to 3 is equal to 5 times py equals to y equals to 5. Right, now using the binomial, the Poisson formula, and the Poisson formula goes like this: Px equals to x is equal to e to the minus lambda, and then it's lambda to the power of x over x factorial. So in these cases, I can write that in these two cases. For this one, it's e to the minus lambda, which is equal to what we're trying to find out. Lambda to the power of 3 over 3 factorial. And then we have that equals to 5, and the probability of y equals 5 using this formula. And then lambda looks a bit strange here. Lambda should go that way, in mind. 5, and then that's lambda equals to y equals to 5. So that's e to the minus lambda, lambda to the power of 5 over 5 factorial. Okay, let's do some obvious cancelling first, and then do a little bit more in a moment so it looks a little bit tidier. First of all, e to the minus lambda cancels, and then we've got lambda cubed cancelling as well, giving lambda squared here now. Right, so I'm just going to, because I don't want to do too much cancelling and then it just looks like a complete mess. So we can then come out and write some numbers down. So we have 1 over 3 factorial, that's 3 times 2 times 1, is equal to 5 over 5 factorial, which is 5 times 3, 5 times 4 times 3 times 2 times 1, lambda squared. Right, again we can do a good deal of cancelling with the numbers here. First of all, we can cancel the 2 5s, and we can cancel the 3, 2 and 1. Well, 1 doesn't need to be there numerically, we'll just put it there just for consistency. So that's 3, 2, 1 there. So we're going to end up with that, with lambda squared equals 4. Lambda squared equals 4. Now lambda can't be negative, so lambda is equal to 2. So that gives us our second answer for B. Now for C, and again another little bit of just calculations to do with no context. Right, we're told that we've got a binomial n 0.4. It says find a value of n such that alpha can be approximated to the normal distribution. Well, all we need to do really is, because the mean is equal to 32, and the standard, the variance is equal to alpha. Now that's what we want, but also using the normal approximation, that's also equal to NP, because the mean of a normal distribution is NP, and the variance is equal to NP1 minus P. So we can say, first of all, NP, so it's n times 0.4, because the mean is 32. The mean of the binomial has got to be the same as the mean of the normal we're approximating it to. So that just gives us 32 divided by 0.4, so that's going to be equal to 80. And then the variance is alpha, but we can say, we know that's also equal to NP1 minus P. So the alpha, which is the variance, is equal to n, which we now know, 80, times P, which is 0.4, times 1 minus P, which is 0.6. So that gives us a value of alpha of 19.2. So that's question 2 done. Let's look at question 3. Okay, so new context again here. Question 3 says a single observation is to be taken from a normal distribution, and it's given us a null hypothesis, an alternative hypothesis, and we want to find a 5% level. So what we need to do is look for the tables to look, and it's a one-tail test. So we're looking on the upper tail only, and the key number that we're looking for is 0.45 to try and find where that number comes from. P equals to greater than 0.45. So we'll have a look for what critical values we will get from the 12 in our tables, looking at the binomial for 12. So here we go, let's go to the tables then. So ensuring that we're looking at the right number of trials, which is 12, and the right probability, which is 0.45. We're looking for numbers here, around here, which go below 5% from the other side. So we're looking for numbers which are above, but the first one, which is above 0.95 here. So I can see this number here is actually below 0.95. And this number here is above 0.95. and the corresponding value here is 8. So what I'd do is I'll go back to the script and then we'll write the probability, the actual thing that this represents, and then manipulate that to get our critical value. Okay, so the number I've just found from the tables is telling us that Px is less than or equal to 8 is equal to 0.9644. So that tells us that that's the same as P1 minus Px is greater than or equal to 9, which is 0.9644. So that's telling us that Px is greater than or equal to 9 is equal to 1 minus 0.9644, which is equal to 0.0356, which is the first one, which is below 5%. Because if you think back, it was the next one would have been above 10% even, as we'll see in a moment. So that means the critical region, okay, it's just that x is greater than or equal to 9. Okay, and that's our critical region for part A. Part B, we've already done it really by the way we set it out. So I set it out. The actual significance level is 0, or better write as a percentage, so that's 3.56%. Okay, so then it says the value of the observation found is 9. State the conclusion that can be made from this. Well, there's only one mark here, so they're not asking for interpretation. There's no context anyway. The critical region is the set of values for which H0 is rejected. Okay, now 9 is in the critical region. So that means reject H0. I'm sure that's all they're looking for. Okay, now part D, a couple of bonus marks really. State whether or not this conclusion would change if the same test was carried out at a 10% significance level. Well, clearly there would be no change. There would be no change because it's still below significance level. Because 0.356, that's right, I don't think they ask it, they just want to give us, but I'm just explaining why. I don't think they're expecting it. Is below 10%. But if we were to go to a 1% significance level, we would then say at this point would change this point H0 would now be accepted. Since, and I'll write that, since 0.0356, this time we've gone above our significance level. So this time we would not be rejecting H0. So that's question 3. Let's have a look at question 4. So we've got because of the constant probability here, we've got the continuous uniform distribution, sometimes called the rectangular distribution. They've actually asked they've asked that as part A. That's because the probability doesn't change. So the probability is constant throughout the range. It isn't, the numbers vary between 2 and 7, but there's nowhere within the range where one is more likely than the other. So a randomly, this is about flight takes off at airport. So it's talking about waiting time. So the waiting time, the least the waiting time can be is 2, and the most it can be is 7. So a randomly selected flight takes off at 9 AM. Find the probability the next flight will take off at 9:05. So what we're being asked for is the probability that X is less than 5. And if we look at if we were to look at the PDF for this, I really don't bother with integrated normally with this type of thing. 2 to 7, we want the probability that it's less than 5. Now looking at that, clearly this here is going to be 3/5 of the area, because the length from here to is 5 and the length from here to here is 3. So we can see clearly that that's equal to 3/5. The area there is 3/5. Okay, now it says find the probability that at least one of the next 5 flights has a waiting time of more than 6 minutes. So this is going to be binomial on top of the continuous uniform distribution. Well, first of all, we're going to need to work out the probability that there's more than 6. The probability that X is more than 6. Again, we can see, looking at our rectangle, we're looking for this probability now, 6, between 6 and 7. Now we can see that that is equal to 1/5. But this is, we're asked for the probability of 5 consecutive times that this happens, or the probability that it happens at least once. Find the probability at least one of the next flights has a waiting time of more than 6 minutes. So we've got 5 of these such flights, so let's call it Y, is binomial with 5 and 1/5. And we're being asked for the probability that Y is greater than or equal to 1, at least 1, which is 1 minus the probability that Y is less than or equal to 1. No, less than or equal to 0, so in other words 0 is there. So Y, which is equal to the probability of this never happening. So that's 4/5 to the power of 5. I don't really think it's helpful to go straight to the formula for the 2 endpoints. It basically, I've seen students writing, things like 5C5 and then 1/5 to the power of 0 and 4/5 to the power of 5, which is of course how the formula works. But that seems to me, I don't know, it seems to me a bit over the top really, when we can see we've got the same thing happening 4 times, okay, consecutively. Similarly, if it had been late all of the time, you'd be if that had happened 5 times, right? Then we'd do 1/5 to the power of 5. So anyway, that's equal to 0.67. If we go to 3 significant figures, 0.672. Okay. Right, so that's part C. Part D says find a cumulative distribution for this. I think I will integrate rather than try and do anything a bit slicker than that, but we're going to integrate. So we've got fx is equal to the integral of 1/5 dx. So fx is equal to 1/5 of x plus c. But we know that f0 equals to is equal to not f0, f2 is equal to 0 because of this number here. It's impossible that the number can be less than 2. So that tells us that 0 is equal to 1/5 times 2 plus c. So that gives me c is equal to minus 2/5. It does say for all x, and want to sometimes they say fully specify the number, the distribution. So find it for all x. So that means that if we write it over here, we have fx is 0 if x is less than 2, and it will be equal to 1/5 of x minus our value of c that we've just found. That's minus 2/5 if x is between 2 and 7, and if x is greater than 1, then it's obviously certain that that's going to be, the number is going to be less than that. So that's x is greater than 7. So that we've fully specified the CDF there from doing that. So that's that question done. Now it's a structured distribution of this. Well, this is linear, so the cumulative distribution function is going to look something like this. The mark scheme says it's not necessary to write the vertical bit here, but anyway, I'll put it in. Now the numbers vary between 2 and 7. The probability of obviously it going upwards as we go that, and then fx comes here, and obviously the probability varying between 0 and 1. So that's our sketch for the probability distribution, the cumulative distribution function. Okay, so part F, it says on foggy days, an extra 2 minutes is added to each waiting time. So in fact, I mean, we could do this by just changing these numbers to 2, 4, and 9 and working from scratch. I'm not going to do it that way, but it would be perfectly okay because we basically got another continuous uniform distribution. I'm going to use combination of random variables, so probably be a little bit quicker. It says on foggy days an extra 2 minutes. So the expected time, so basically we're being asked for e of x plus 2. So this is the expected time on foggy day. Day will be equal to that, which is equal to ex plus 2. Now e is just the average of the two values, so it was 2 and 7, 2 plus 7 divided by 2 plus 2. So that will be equal to 9 over 2, which is 4.5, plus 2, which is 6.5. Or, as I say, you could have just found the average between 9 and 4. And that would have got you 6.5 as well. Now the variance of x plus 2 is equal to the variance of x, because adding numbers to a set of numbers doesn't change the variance. And there is a special formula which is in the formula book for the variance of a continuous uniform is equal to b minus a squared over 12. So that basically is 7 to the two end values squared divided by 12, which is equal to 25 over 12. So that's now question 4 done. So question 5 is a sampling distribution question. It's actually a probability question really, because we're given the ratios. Well, we're given them as R, Q, R and S as the ratios of these 1 pence, 5 pence and 10 pence coins. And the sampling distribution that we have here is, it says that the value is of the highest coin. Anyway, more of that in a moment. Let's do part A first, which is just simply to list all the possible samples of 2 coins which may be selected. Well, of course you can have 1, 1. And we could also have 1, 5. It's not necessary to write 5, 1 as a different one, but I'm going to write times 2 for reference in the next part. And also we can have 1, 10, and again I'll just write times 2 because we've also got 10, 1. And then, so that's all the ones with the 1 in them. And then we've also got 5, 5, of course. And we have 5, 1's already taken, so we've got 5, 10. And we've got 2 variations of that because we also got 10, 5. And then in addition to that, we've got 10, 10. Okay, that's the combinations. Right, now that's part A. Now it's about, we've got quite a few more marks available for part B, 7 marks, and it's basically to work out Q, R and S from these numbers here. Okay, well, we've got enough, I think, here. In order to get a value of the sample induction of 1, that can only come from 1, 1. So, and that's got probability for 1 pence coin of Q. Okay, so that means that Q squared equals 1 over 25, which clearly means that Q is 1 over 5. But to get 5, we've got a number of possibilities. We could have 5 and 5, which has got probability, let's get the letters the right way around, R. So that's R squared. But we could also have a 5 and a 1. It just can't have a 10 in it. And that will have 2 times Q times by R, but we know that Q is 1/5, so that's 2/5 of R. Okay, so we know that the total of these two must be equal to the 13 to 40 that we have there. So that means that R squared plus 2/5 of R is equal to 13 out of 80. So I'm going to times through by 80. We have 80r squared, and then that's plus 32r equals to 13, so that's minus 13 equals 0, which looks unpromising. You can use a formula or whatever to solve it, but I tend to like to factorise when I can. It may look unpromising, but it's perhaps not as bad as it looks, because you have a sense it's got to be a whole number of some kind. So if we, especially since we know that one is 13 and one is 1, so it's just about playing with the r number here in order to get 32. So it's looking like, you say we need to get to 42, so look, just trying to play with the numbers, we can come up with 4r here and 20r here, this one being plus, so that's the one that doesn't count, and this one being minus, r equals to quarter, but you don't have to feel like you need to factorise it. Now, to get the value of these, it's probably, we could do the similar process here and work out a slightly more complicated equation, because there'll be combinations. We'd have to add these two combinations and this one, so there'll be 3 combinations to add. This one, and this one. So it's probably quicker and easier to use the fact that these have got to add up to 1, because it's a probability distribution. So we can use Q plus R plus S equals 1. So Q, which is 1/5, R, which is 1/4, plus S is equal to 1/20. So putting over a common denominator here, that gives me 4 plus, that's 9/20, 4/20 plus 5/20, which is 9/20. So looking at those, we have, oh, not 1, it's not 1/20, it's 1. So looking at that, we have S is equal to 11/20. Okay, that's that question done, 5 marks. So let's have a look at the next question. 7 marks. Let's look at the next question anyway. Okay, so it's another continuous random variable question. This time we've been given a PDF fx and we're told that the mode is 1. Now I note a few things here, that the mode is the highest point, of a PDF. Okay. Now, it's not necessarily to differentiate, because obviously to do it, because it could be at the highest point of some PDFs, for example, this one, and differentiation is obviously not appropriate, or even other things which have involve curves. You know, if we had a quadratic, it could be like that, and you know, we'd be doing that. But I note a few things. This is a kind of upside down quadratic like that from a curve, and the mode's in the middle. So in this case, the highest point will be when f stroke 1, which is the mode, because the mode is 1. F stroke 1 is going to be equal to 0. So that, but f stroke x is equal to a minus 2bx. So f stroke 1 is equal to 0, implies that 0 is equal to a minus 2b times 1. So that gives us a equals 2b as required. Okay, so that's part A of the question. Part B, says find the values of A and B. Well, the other key feature, one of the key features of the PDF, well, obviously it can't be negative, but that's not relevant here because clearly it won't be, is that the area underneath is equal to 1. So area underneath equals 1. So we have the integral from 2 to 0. Now we know that A is 2b, so let's write that in. 2b x minus bx squared dx equals to 1. So that means that bx squared minus 1/3 bx cubed from 3 to 0 equals 1. So, from 2 to 0, so to say. So that means that b times 2 squared minus 1/3 b times 2 cubed equals 1. So 4b minus 8/3b equals to 1. So that gives me 12, that gives me that b equals to 3/4, I think. Well, that's right, not Ross. So that's 12 minus 4/3b equals 1. So b equals 3/4. That means also that A is double that. So that's 3/2. Okay. Now for part C, it wants f of 1.5. Capital F of 1.5. F, that's CDF. So f of 1.5 is equal to probability that x is less than 1.5. So although you might be tempted to work out f, they're only really asking for a probability, and there's only a couple of marks. So let's just go to our our PDF, which we now know. If we go back to we now know the actual function for the PDF here, because we know A is 3/2 and B is 3/4. So that's of 3/2x minus 3/4 x squared dx, which equals to 3/4 x squared minus 3/12 x cubed, just integrating those two terms between 1.5 and 0, which is equal to 3/4 times 1.5 squared minus 3/12 times 1.5 cubed. And obviously the zero limit will just come to 0. So that comes to, as a fraction, 27/32, which is, if we work out the number, 0.844. Okay. Then part D, it says state whether the upper quartile of x is greater than 1.5, equal to 1.5, or less than 1.5. Now, for the upper quartile, let's call it Q3, f of Q3 equals to 0.75. But we know that f of 1.5 is equal to 0.844. So therefore, since 0.75 is less than 0.844, okay, that must mean that the lower quartile must come before the 1.5. So that means that Q3 is less than 1.5. Less than 1.5. So that's it, just one more question to go for this paper. So question 7 starts off with a binomial. In fact, it's binomial for most of the question, and then there's an approximation at the end. The thing here is it's given us a random sample of n, so we've got an unknown n, but it tells us that the standard deviation is 1.4. So we know that the variance of a normal distribution, so we know it's not normal, it's a binomial distribution. We know that the variance of a binomial distribution of NP is NP1 minus P. Okay, well, that means that we're given the variance of 1.44, so we have 1.44 squared, because the variance is standard deviation squared, times by n, times by 0.04 times 1 minus 0.04, which is 0.96. Okay, so that gives us n is equal to 1.44 squared over 0.04 times 0.96, and that comes to 54. So that's A1 done. A2, well, we know that the mean, or the expectation, is equal to NP, so that's equal to 54 times by 0.04, so that equals to 2.16. Okay, now we have for part B, it's now a binomial that we know with 20 trials 0.04, and we find the probability all of these pass the emission test. That's basically the probability that x is 0. Okay, so basically I don't think it's helpful or necessary to just revert to the formula like NCR, because we know there's only one combination, and that's 0.96. Now it's failed 20 times. There's only one way of doing that. So failed or passed 20 times, which means 1 minus that, because that's the probability of failing. Okay, that comes to 0.442 to 3 significant figures. Okay, now then there's a conditional probability question. It says given that at least one of these cars fails. So let's work that out. Find the probability that at least one car fails. So that's probability that x is greater than or equal to 1 is equal to 1 minus the probability of x equals to 0. And that equals to 0.5579. And I've actually stored that number on my calculator because we need that for the next part. Okay, so that's the probability that at least one fails the admission test. Sorry. Now, it says find the probability that exactly 3 of these cars failed the admission test, given that we know that this has happened. Well, now, some people know this kind of intuitively, that it's going to involve dividing by this, because we can consider this the full. We're now certain this happens, so we divide by that. But let's just use the language of conditional probability for those who like that kind of thing to hang on. Right, so the formula we're looking for is the probability that A conditional on B, P A intersection B over PB. So if we call, this is the conditional bit here, so if we can think of that as event B in this context. And what we need to find out is what the probability of x is equal to 3 is, with no restriction at all. Basically, what the probability of it happening, whether this happens or not. And that's just binomial. We can just use NCR, so that's 20C3. It happens 3 times, so that's 0.04 to the power of 3, which means it doesn't happen 17 times, or the other way around, whatever. Well, those are the numbers correct. So it basically fails 3 times and doesn't fail, in other words, passes 17 times. That equals to, let's work out 20C3. 20C3 is 1140 times that. Which is 0.96 to the power of 17. That equals to 0.03644 and so on, 98 and so on. I've stored that number on my calculator as well. So now to the conditional probability part of this. We are being asked to find out what the probability of x is equal to 3, given that given that we know that x is greater than or equal to 1. So that's the same as the probability of both of these occurring, but as we'll see in a sec, I don't need to write it like I'm just writing it now. Just trying to relate it to this formula that some people like to use. Some people can just intuitively divide by this number and just come up with it, which is fine. So x equals 3 and x is greater than or equal 1, divided by the probability that B happens, which and B is, in this case, the probability that x equals to 3. Now, here's the thing. In this case, we've got a case where one set is actually inside another set. In other words, if x is greater than or equal to 1, then maybe reverse this. If x is equal to 3, then we know already that x is greater than or equal to 1 anyway, because that's definitely the case. So, in fact, in this case, because we've got x equals to 3, the intersection basically is the middle. If we call this a set x equals to 3, and then this is a set x is greater than or equal to 1, if we're in this set, then we're in the outer one as well. So, so that's... So my apologies, of course, B is the event probability that x is greater than or equal to 1 here. So it's basically these numbers divided by each other. So that's 0.036449 divided by 0.5579. And like I say, I've got those numbers stored on my calculator, but to 3 significant figures, that comes to 0.0653. Okay, so that's part D done. it's got part C done, so they say. Let's now go to part D, and then that's the paper complete. So we finish off with a hypothesis test using a approximation. The null hypothesis here, as it always is in these situations, is that there's no change and that it's 4%. The null hypothesis should always have equality no matter what the words are. The null hypothesis in these questions is always that there's no change in probability. The alternative hypothesis is that we've got a change, but it's actually, in this case, it's specific. It's a one-tailed test that it's more than 4%. So that's P is greater than 0.04. Okay, now our original distribution was binomial with 125 now, because it tells us it's 125. 0.04. Now that is not helpful in trying to work out the hypothesis, because the actual to do the calculation, because the actual sample size is very large here, so it's going to be quite cumbersome, because we've got 10 as our test statistic, so we wouldn't want to be testing all the values from 10 to 125, or even just taking it one, take away the other. It'd just be a lot of calculations to do. So what we do is we use a suitable approximation. Now this time it's Poisson. We can let lambda equal to, so it's going to be approximately Poisson, with lambda being equal to 125 times 0.04, and that number comes to 5. So it's approximately Poisson 5. Okay, we wouldn't use the normal approximation here because the probability is really very small, so Poisson is ideal. Now, so we're going to use Poisson, and we're going to work out the probability of our test statistic happening. Okay, assuming H0, so the probability that X is greater than or equal to 10, assuming that P equals to 0.04. Okay, so assuming the null hypothesis, basically. That is approximately equal to 1 minus, well, it's not exactly, it's equal to 1 minus probability that X is less than or equal to 9, which is approximately equal to 1 minus the number from the Poisson table, the cumulative number, which I'll look up in a moment, of less than or equal to 5, with from the Poisson, less than or equal to 9 with a Poisson value lambda 5. So we have Poisson 5 here from the tables, and we're looking at the probability that there's less than or equal to 9, which is 0.9682. 0.9682, and that equals to 0.0318, and this is when we need to look at our significance level, which is 5%, so this is less than 5%. Okay, so that means that we reject H0, except H1. There is evidence to support the mechanics claim. Now, looking at the mark scheme, that in itself was enough, but I do think we need to be careful here. So I'm going to write a bit more just to nail it on. So we write we actually write what the mechanics claim is as well, and that is that the claims that more than 4% of cars at the garage apologies, it's a sunny morning, I can't actually read the thing that's on my screen. So the mechanics claim is that the more than 4% of cars tested at the garage chain are failing and missing the test, so that the number of cars failing the emissions test is increased or is more. There we go, we've actually got the mark twice here. They're not going to give us twice, but it's probably a good idea to totally nail it on with these word questions. Certainly you're not going to get it for just saying reject H0. That's it. Okay, that was that paper done. Hope you found it useful, and goodbye.